everyone, Mrs. Hanson again. Boy, oh boy, this chapter just keeps getting more fun, doesn't it? We started investigating patterns of chemical change and learned how to balance equations. We then turned into a quantitative chapter by introducing the mole and using a mole map to do some conversions. And now really we have a beautiful blend of both coming at the end. Looking at a balanced chemical equation in terms of moles, letting us read a recipe card. So a balanced chemical equation tells us how many moles of each reactant combine and the number of moles of each product that form. The moles in a chemical calculation. What I just wanted to share is what coefficients truly mean. When I see 1 in front of a nitrogen molecule, we can read that as one molecular compound, one molecule of nitrogen, or an entire mole's worth of nitrogen molecules. They combine with one molecule of oxygen to form 2 molecules of NO. Coefficients stand for individual molecules, or it can stand for a whole mole's worth of molecules, and that's a much more practical thing. So we use these mole ratios as conversion factors to convert from one mole of a compound into the other, where the coefficients themselves become conversion factors. You look at a balanced equation as a recipe card. If we see that our balanced equation gives us 1 molecule of nitrogen, 1 mole of nitrogen, plus 1 mole of oxygen to form 2 moles of NO. What are those relationships? I could see that for every 1 mole of nitrogen, 1 mole of oxygen is required. I could see for every 1 mole of nitrogen, we produce 2 moles of NO. And I could also compare an oxygen to the product as well. All of these different mole ratios that are allowing us to convert from one unit to another from a balanced equation. I want you to consider the mole map that we were just practicing with the mole as the central calculation. If I'm weighing, I head into the mole using molar mass. If I'm counting, I head into the mole using Avogadro's number. All road leads into the mole. The same is true for our stoichiometry roadmap. Stoichiometry is the quantitative study of chemical reactions. Quantitative study. And that's what this is, the chemistry stoichiometry roadmap, where the road leads into the moles. This is our mole ratio, the heart of all of our problems, the mole ratio, our want over given stoichiometric ratio. Now notice, I can count, I can weigh, or I can take a volume, the 3 ways that we measure matter. We count it, we weigh it, or we take a volume. All roads lead into the mole, just like down here. We know to use Avogadro's number if I'm heading into the mole from counting. I know to use molar mass if I'm heading into the mole from the scale. And when we get to the gas laws, we'll learn the molar volume. If I'm given a volume, we can use our molar volume to convert to the mole. Just like molar mass, we have molar volume when we get there. When we're heading back out of the mole, we know to multiply. Multiply by Avogadro to get to particles. Multiply by molar mass to get to grams. Our 3 steps to stoichiometry: we divide, we ratio, we multiply. Those 3 steps allows us to convert between any ratios from a balanced chemical equation. As usual, it makes more sense if we dive in and just start doing some examples. When we look at a balanced equation, such as carbon monoxide, a poisonous gas that combines with hemoglobin in the blood, it reduces the amount of oxygen that can be delivered to tissues. So that's why you should never run your car in your garage with the door down. There's plenty of oxygen in the room, but the hemoglobin cannot combine to the oxygen because it has a higher affinity for carbon monoxide. When ethane, C2H6, is burned in the presence of oxygen, O2, the balanced equation is shown to us with 2 moles of C2H2 reacting with 5 moles of oxygen in the presence of heat. Remember, the triangle over the arrow means heat. We get 4 moles of carbon monoxide forming and 6 moles of water formed. Using this balanced equation, this 2 to 5 to 4 to 6, how many moles of CO that's what we want to know, are produced from 3.5 moles of ethane. That's our given. See what we're doing on our mole map? Given a mole, we want to calculate a mole. Now we call these a mole-mole problem. Pretty snappy, right? A mole-mole. Given a mole, calculate a mole. And the coefficients, the coefficients serve as our conversion factor, the heart of our stoichiometry roadmap, the want over given coefficient ratio, since coefficients stand for moles. We use the coefficients as a conversion factor. Now, since I'm at the mole, I don't need the first step. I wasn't given grams or particles or volume, and I only want to go as to the far as the mole, so I don't need the third step. It's just the heart of the problem, the want over given. So we're not needing the first step or the third step in our 3-step problem because we're not asked to go out that far. Given a mole, calculate a mole. It's a 1-step heart of the problem stoichiometry. Start by writing what was given. We were given 3.5 moles of C2H6. We need a conversion factor, the heart of our problem, our want over given mole ratio. And remember what we wanted to solve for? We wanted moles of CO. I'd like to know how many moles of carbon monoxide form if given 3.5 moles of the original C2H6. We want to know CO. Its coefficient is 4. We were given C2H6. Its coefficient is 2. The coefficients become the conversion factor. In a stoichiometry mole-mole problem, we use the balanced chemical equation to find the coefficients of what we want over given. So on your calculator, we would solve this by saying 3.5 times 4 over 2, and we get 7. 7 moles of CO will form. Hey, we just did our first mole-mole problem. Let's try another. Here's an example. Whoops, I have to flip our notepad page. Where the recipe gives us 1 mole of nitrogen to react with 1 mole of molecular oxygen, and it forms in the presence of heat 2 moles of NO. Coefficients stand for moles. These are mole-mole problems. Given a mole, calculate a mole. And in order to do that, we're right smack in the heart of our stoichiometry roadmap. We ratio. We use our coefficients of want over given. Given a mole, calculate a mole. These are mole-mole problems. How many moles of NO are formed if 3.3 moles of N2 were to react? Like say, I know the perfect ratio is 1 to 2 from our balanced equation. What if we change one of them? What did the others do to keep the equation balanced? Start by writing the number you were given. We were given 3.3 moles of N2. What is it that we want to solve? And what is it that we were given? We're in the heart of our problem, the want over given stoichiometric ratio, mole ratio, where the coefficients are used as conversion factors. We want to know NO. Its coefficient is a 2. We were given moles of nitrogen. Its coefficient is a 1. So our mole ratio is 2 over 1. 3.3 times 2 over 1, and that's 6.6 moles of NO. So let's look at letter B. This time we're starting with 0.5 moles of molecular oxygen. What would the conversion factor be now to get us out to NO? We want over given. We want to know moles of NO. Its coefficient is a 2. This time we're starting at the oxygen, but it also had a coefficient of a 1. 0.5 times 2 is 2.5. And we have one more I'm going to put down here. If I have 1.2 moles of molecular nitrogen, this is my given. And I want to know oxygen. So just kind of keeping tabs. This time we have a new target. I want to know oxygen from nitrogen. So I go into the balanced equation and I find that both of those have coefficients of 1. So that calculation gives me the exact same answer back. For every 1.2 moles of nitrogen, you would also require 1.2 moles of nitrogen, of oxygen. Both of them are the same number. That was easy enough. Here's an equation where we start with 3 moles of molecular oxygen, and in the presence of sunlight, it converts to ozone, and ozone is O3. In the upper atmosphere, high energy radiation from the sun converts oxygen into ozone. Using this balanced equation, let's calculate how many grams of ozone are formed from 9 moles of oxygen. Now look at your stoichiometry roadmap. You have one of these in your notepad. You're going to be provided one of these in your test-taking tool page. Where are we given? We're at the unit mole, so we're right here. We're at 9 moles of oxygen. What do we want to know? We want to know grams of ozone. So what kind of steps will be involved now? I know that the heart of my stoichiometry roadmap is my want over given coefficient ratio. But I need to go one step further to get out to the grams of ozone. So we're going to need to, remember the first step is always divide. If I need to head into the mole, I divide. I don't here because I'm already at the mole, so I'm not needing step 1. But I will always ratio. That's always a given in the heart of a stoichiometry problem. But I will need a step 3 that will multiply to head out to the grams. So let's think about that. Given 9 moles of oxygen, that's me standing right here, I want to convert that to moles of ozone. And that's our want over given ratio. That's the heart of our problem. What is it that we want? What is it that we started the problem? What we were given? And remember, these are coefficients that are a conversion factor. We want to know ozone. Ozone had a coefficient of 2. We started from oxygen. Oxygen had a coefficient of 3. That first conversion factor ended from moles of given, and now I'm standing right here, moles of want. One more step to get to grams, and notice that that's the molar mass of what we want. We want to know grams of O3. So the molar mass of O3 is 48. 16 times 3 is 48 grams of ozone in every 1 mole. So remember the mole map. To go from moles out to grams, that conversion factor is called molar mass. So we start with our 9 moles of oxygen. We multiply by a coefficient ratio of want over given, 2 over 3. And we'll multiply by molar mass of 48. And my screen reads 288 grams of ozone were formed. For every 9 moles of oxygen, 288 grams of ozone form. You just did what would be called a mole mass problem. Given a mole, calculate a mass. We started here and ended here, a 2-step conversion problem. Let's keep another one going. This one talks about wine being produced by the fermentation of grapes. In fermentation, the carbohydrate glucose, C6H12O6, is converted into ethanol, that's drinking alcohol, and carbon dioxide according to the given balanced equation. For every 1 mole of glucose, 2 moles of ethanol form, and 2 moles of carbon dioxide form, a 1 to 2 to 2. How many grams of ethanol? Well, I'm going to just make a note. That's my target. That's what I want to know, is the mass of ethanol. They're produced from 5 moles of glucose. So I'm starting here. I'm given the moles of glucose. And what do we want? Oh, we want mass in grams. What do we have? We have a step where we need our conversion, our want over given, coefficient conversion factor. And then we'll need molar mass to convert out to the other grams. So we'll need a ratio, and then we'll need a multiply. Start by writing our unit, 5 moles of glucose. We need a coefficient ratio of want over given, the heart of our stoichiometry problem. We want to know ethanol. Its coefficient is a 2. We started with glucose. Its coefficient was 1. That brings us from moles of given to moles of want. So now here I'm standing at the moles of want. I have another step though. I got to get out to grams. And I literally trip over my conversion factor, which is molar mass. And see how nice they were? They gave that to us in the story problem. 46.07 grams is the molar mass of C2H6O for every 1 mole. So we start by our mole quantity of 5. We multiply by our mole ratio of 2 over 1. And we're going to multiply by the molar mass of 46.07. And my screen reads 460.7 grams of C2H6O. We ratioed, we multiplied to solve that stoichiometry problem. We were given a mole and asked to calculate a mass. We call those mole mass problems. Let's do another. Here's a balanced equation in which ethanol reacts with oxygen to form carbon dioxide and water. Our mole ratio for every 1 to 3 makes 2 to 3. Coefficients are moles. Letter A, how many grams of carbon dioxide, starting with 0.5 moles of ethanol? I really would encourage you to pause, process this information, give yourself think time, try these 3 problems, and only come back when ready to check your work. Please give yourself the practice. All right, here's the heart of our problem, the want over given coefficient ratio. Our heart of our problem. We want over given, where coefficients become the conversion factor. Letter A gave us 0.5 moles of ethanol, C2H6O. We want to know grams of carbon dioxide. I know that it will require 2 conversion factors, so I'm just going to get those ready so I can see my target. I want to get to grams of CO2. Given a mole, we want a gram. These are called mole mass problems. Step 1, we need a mole ratio to convert from what we want over given. The coefficient of what we want, carbon dioxide, is a 2. The coefficient of what we were given is a 1. So the mole ratio of 2 over 1 brings me from moles of given to moles of want. So now I'm standing right here. I need one more step, and that's to get out to grams. We know that converting from moles to grams requires the molar mass as your conversion unit. The molar mass of carbon and oxygen, that gives me 32 and 12, that's 44.01 grams. Let's hit that out and see what we find. 0.5 times 2 over 1 times 44.01 is 44.01 grams. I'm embarrassed I hit that. It's the same number, 44.01 grams of carbon dioxide. Did you find that as well? Letter B gave us 2.4 moles of ethanol. But this time we wanted to know water. So with water's want over given ratio, we want to know water. Its coefficient is a 3. The coefficient of ethanol, still a 1. And in the next step, since we want to know water, we need to know its molar mass. So we have a new target this time. 2 H's added to an O, 18.02 grams for the molar mass of water. 2.4 times 3 times the molar mass of 18.02, and my screen reads 129.7. Well, use 2 decimals, 0.74 grams of water. Maybe I should have just 1 decimal. And in letter C, 0.25 moles of ethanol, and we want to know grams of oxygen. So the oxygen coefficient is a 3. Coefficient of your ethanol is still 1. And this time, to get out to grams, we need the molar mass of molecular oxygen. So that's 32 grams of O2 in every 1 mole. 16 taken twice is 32. 0.25 times 3 times the molar mass of 32, and you found 24 grams of oxygen. How did you do? Oh, I hope these are getting easier. Ooh, here, I was just kind of reading ahead. We have ethylene reacting with water to form ethanol. These are all balanced with coefficients of 1. Ethanol, C2H6O. This has a molar mass of 46.07 grams per mole. I'm just kind of tabulating the information in the problem. It's synthesized by reacting ethylene. So ethylene is over here, 28.05 is the molar mass. So that's those numbers there. How many grams of ethanol are formed? That's what I want to know, is how many grams of this, that's my want, given 14 grams of ethylene. So that's my given. Look at this fun. All right, what are we doing? You see where we're starting? We're way over here. We're at the mass of given. What do we want? We want to know a mass of the product. We're going to call these mass products. Mass problems. Given a mass, calculate a mass. We will need all 3 steps of stoichiometry. We need to divide to get into the mole. We'll then use the heart of our stoichiometry problem and do a want over given mole ratio. Then we'll need a step 3 to get back out to the grams of what we want. We'll divide, we'll ratio, we'll multiply. So let's start by writing what we're given. We had 14 grams, I'll do it right here, 14 grams of ethylene. That's C2H4. That's me standing right here, the mass of what is given. The first conversion factor needs molar mass to bring me from mass to moles. It's an old mole map problem. We know that 1 mole of C2H4 has a molar mass of 28.05 grams. That was given to me. Now I'm going to just get my 3 parentheses ready. I know it's a 3-step conversion, and I just want to get those 3 parentheses ready so you can see where we're trying to get. We want grams of ethanol, C2H6O. That's why we're given a mass. We want to calculate a mass. That's why these are referred to as mass problems. When you have to use the entire roadmap, you need 3 steps, 3 conversion factors. We divide by molar mass of given. We use the coefficient of want over given in your mole ratio. And then we multiply by the molar mass of the new compound that we want. Divide by given, ratio, multiply by want. All right, let's take a look. Step 1, we divided by 28 the molar mass of given. Now here's where we're standing. I need the mole ratio to pass through this step. I'm tripping over my conversion. What do we want? Well, we want ethanol. Its coefficient is a 1. We were given ethylene. Its coefficient was also a 1. So that's nice. A 1 over 1. Want over given mole ratio. So now I'm standing here. I have one more step to get out to the grams of what we want. And so that relies on the molar mass of where we're heading to, which is C2H6O. And its molar mass was given as 46.02 grams. We did it. 3 steps. Let's hit 14. We divide by the molar mass of given, 28.05. We ratio, which is 1 over 1. And then we multiply by molar mass of where we're heading, the 46.02 grams. This would yield 22.968, 97 if we round, about 23 grams of C2H6O. Given a mass, you calculate a mass by dividing, ratio, multiply. The 3 steps of stoichiometry. You divided, you ratioed, you multiplied. That brings us straight across the stoichiometry roadmap. Let's try another. I think the more we do, the better you get. I'll model one more and then ask you to try some on your own and come back. Here we have a balanced equation of salicylic acid reacting with acetic acid, forming aspirin and water. The coefficients are all ones. 7, 8, 9, 9, 8. They are indeed. This is a balanced equation and the coefficients are all ones. That's pretty nice. How many grams of aspirin form? How many grams of aspirin form if 10 grams of salicylic acid are started? Given a mass, calculate a mass. The 3 steps of stoichiometry. Start here and end here, knowing at the heart of your problem is your coefficient ratio of want over given. To move from mass to mole, the conversion factor is molar mass. We'll need the molar mass of C7H6O3. Let's go to work on that. Carbon 12.01 times 7 plus 1.01 times 6 for the oxygen plus 16 times 3 for the oxygen, so that's 138.13 grams. We're going to need a molar mass of aspirin as well, C9H8O4. Let me work on that. 12.01 times 9 for the carbon, plus 1.01 times 8 for the hydrogen, plus 16 times 4 on the oxygen. Oh, I didn't hit that right. It didn't look right. I hit plus, times 9, plus 1.01 times 8, plus 16 times the 64. Yep, there it is. 180.17 grams per mole. All right, that's been out there before. We've used that one. That's why I knew it didn't sound right. Here's what we're starting with. 10 grams of salicylic acid. My first step is to move from grams to moles. I literally trip over my conversion factor. I know that 1 mole of C7H6O3 would weigh 138.13 grams. That's my conversion factor, the molar mass. We're now at the heart of our stoichiometry problem. What is it that we want from the given using coefficients as our conversion factors? Well, this was nice. We said 1 mole of aspirin is equivalent to saying 1 mole of salicylic acid. Couldn't be any nicer than a 1-to-1 mole ratio. That brought us from here to here. So I'm standing right here. I need one more step, and that's to come out to the grams. And remember, we need molar mass to convert from moles out to grams. We divide, we ratio, we multiply. In 1 mole of your aspirin, it would weigh 180.17 grams. Now we're ready. 10 divided by 138.13 times 1 over 1 times 180.17. And that answer is 13.04. And that's grams of aspirin. Now I've modeled many mass problems. I'd like you to try 3 more on your own and then just come back when ready. As a matter of fact, I think you have many to practice. I want you to turn this video off and I want you to finish page 10. That's where you are now. Finish up page 10. I want you to work all of page 11. And I want you to do up to page 12 where you see percent yield. Come back when you're ready to check. Are you ready to check? It probably took you a great deal of time in order to work through these, and I don't want you to cheat yourself. I want you to practice. So let's do some together. Letter A. I have 55.5 grams of salicylic acid. That's C7H6O3. I want to know grams of aspirin that will form. So it's very similar to the one we modeled. We know that 1 mole of C7H6O3, the salicylic acid, has a molar mass of 138.13 grams. That's my divide to head into the mole. All these coefficients are 1. It couldn't be any simpler. 1 mole of aspirin, I'll just write out its formula, which would be C9H8O4, forms from every 1 mole of C7H6O3. We want to know grams of aspirin, so we use its molar mass in this step. And when you hit, you divide, you ratioed, you multiplied. So I'm going to hit that, see if we got a common answer. 55.5 divided by 138.13 times 1 over 1 times 180.17. My screen says 72.39, and that would be grams of aspirin. I'm just trying to find out where my tiles went. There they are. Let's put letter B here. I don't know what's happening. All right, so letter B just simply says how many grams of acetic acid, that's the other reactant, are reacting with 55 grams of salicylic acid. So I'm going to need just quickly to C2H4O2. Let me find its molar mass. 12.01 times 2 plus 1.01 times 4 plus 32 from the oxygen. So there's its molar mass. So in letter B, we have the same starting point, don't we? 55.5 grams of salicylic acid. And so I know that my first step will be to convert using 138.13. It's still a 1 mole to 1 mole ratio. It's just that now we're going to acetic acid, C2H4O2. Step 3, I have to come down here and I'm going to use the molar mass I just solved for, 50.05 grams. .5 grams of salicylic acid. Divide by the molar mass of 138.13. The mole ratio is 1 over 1. We'll multiply by 50.05, the molar mass of acetic acid. And I found 20.15 grams of C2H4O2. This might be wrong. 12 times 2 is 24, plus 4 on the hydrogens, plus 32. Yeah, that's 60 grams. I just thought that looked wrong. Did you catch that? I'm so glad you helped me find that, because I knew that that wasn't the right answer, and I was able to pull out my mistake right away. This is 60 grams of acetic acid. I bet you're glad I fixed that so that you weren't going crazy. That's the correct answer all along. Let me now repair mine, and you can kind of compare without changing yours. .5 divided by 138.13 times 60. And that's the right answer. 24.1 grams of acetic acid. Good work. Takes a village. And in letter C, if I consider what letter C is asking, let me just bring that over. We want to figure out grams of water. And so the only thing that's going to change is that last step in which we compare 55.5 grams of our initial compound. We know that it will have the same first step over and over. We're starting with the same ingredient. We know that all the coefficients are 1s. Even the water had a coefficient of 1. But the only change now is the molar mass of water will be used in the last step. So all of that repeats, leading out to a new final answer, 55.5 divided by 138.13 times 18, the molar mass of water. And just to let you compare, 7.23 grams of water for part C. The next question used an equation of 1 nitrogen plus 1 oxygen yields 2 NOs. These are all mass problems. So you can see you're going straight across the stoichiometry roadmap. You divide, you ratio, you multiply. In letter A, we're given 10 grams of nitrogen. We use the molecular weight of nitrogen. 2 N's added together is 28 grams. We're at the heart of our stoichiometry problem. We want to know NO. Its coefficient is a 2. Starting from moles of nitrogen, its coefficient is a 1. Here now, 14 plus 16, that gives us a molar mass of 30 grams of NO in every 1 mole of NO. Did you get an answer? Let me catch up. 10 divided by 28 times 2 over 1 times 30. My answer reads 21.4, I'll say 0.4, that's good, grams of NO. We're going to start with 10 grams of oxygen in letter B. We use the molar mass of oxygen to convert it to a mole. 32 grams is the addition of 2 oxygens. We're in the heart of our stoichiometry problem, the want over given ratio. We want to know moles of NO. Its coefficient is a 2, starting with oxygen, whose coefficient is a 1. The nitrogen oxide molar mass was 28. No, it was 30, right up here. 30 grams. We divide, we ratio, we multiply. 10 over 32 times 2 times 30. See what we've done? Mass divided by molar mass. That's our step 1. We divided. Step 2, we ratioed. We want over given coefficient ratio. Step 3, we used the molar mass of what we want, and we did 3 conversions. Mass to mole, mole-mole ratio, mole out to gram. 3 steps of stoichiometry. 10 over 32 times 2 times 30. My screen reads 18.75 grams of NO. Letter C. This time you started with 10 grams of nitrogen. Nitrogen with its molar mass of 28. We want to know oxygen. Its coefficient is a 1, just like the mole of nitrogen, a 1-to-1 stoichiometric ratio. The molar mass of oxygen is used in the last step. So 10 over 28 times 32. 11.42 grams of oxygen. You did it. What's next? Well, you made it through all of your practices there, didn't you? Let's see. This is a good time to end the lesson just to make sure you're giving yourself time to process. The next section is on percent yield, and it would be a good time to just pause, take a break, work some additional problems, come back to the last part. We'll do percent yields, and then we still have one more section, the limiting and excess reagents. This chapter is loaded with good stuff. Good work so far, team.